hear the audio? I'm guessing they can, because I can see. Okay. Joe, could you put your thumbs up if you can hear us? Okay, oh, thumbs up from across the room. Okay, super. Okay. Well, it's a great pleasure to be able to introduce a talk in person, and I hope that we can resume this again very soon. Jostein is going to talk us through a fantastically interesting concept around heavy lift drones. It's a technology that he's been working on for several years now, and it's really starting to get to the point of some very exciting prototypes. And I think I will leave the rest of the talk, because we're slightly behind, to his capable introduction. So thank you very much, and I look forward very much to the presentation. And apologies again for the delay in getting started. I'm afraid it's more challenging than I'd like it. Thank you.
Thank you very much. Let me quickly get the presentation up. Good evening. There's a lot of exciting stuff happening in the field of drones, especially around the personal transport drones. And I put a collection of pictures up there, and it's quite difficult not to be carried away and excited seeing all these new developments. And sometimes you might ask yourself, is this really the next revolution after the smartphone? Is it just a couple of years from now that you will go home from this event with an Uber Air being flown home in an autonomous vehicle, and your parcel delivery from Amazon and then terminal arrives within 10 minutes of the order being placed? And before we look at what we're doing at Flowcopter, I thought it might be more interesting to try to answer this question. And I have prepared some slides for you to look at the anatomy of these devices to see what's actually possible with today's technology. Quickly introduce myself. My name is Uwe Stein, Technical Director at Flowcopter.com. You might have heard out from the accent, I'm not from Scotland. I grew up in North Germany. I got excited about renewable energy there, studied near Frankfurt, and came over to Scotland in 1995, inspired by the work from Stephen Salter in the field of wave power. I then joined the newly started company Artemis and spent the next 2 decades developing a new hydraulic transmission technology that we are now using in Flowcopter. And towards the end of this development at Artemis, one of my colleagues came up with this great idea to use this technology in drones. Of course, initially kind of smiling at the idea, thinking hydraulics and drones not necessarily a good mix. We concluded that it's actually very applicable, and we did start the work on a hydrostatic transmission for a drone. I'm going to come back to this later in the talk, but first, let's try to answer the question, are we just a couple of years away from having air mobility from drones? Is this the next revolution after the smartphone? Or is it one of these fuel cell or fusion reactor technologies that's always 10 years out? And in 10 years, we're still looking at the new technology that's just about to come. So we're going to look at this first. Then we're going to move on to the Flowcopter work on the drone. And at the end, I want to talk a little bit about the markets we're trying to address with this. Most of you will think when it comes to vertical takeoff and landing aircraft about helicopters, as they've been around for about a century. You can see a very old one and a modern one on the left. What might be slightly more surprising to you is that actually before helicopters, people were building quadcopter drones. As you can see there in 1923, actually so 10, 15 years ahead of the first commercially viable helicopter. And at the time, it might have seemed easier to have 4 props lifting you up, controlling the pitch on each of the 4 rotors. But it turned out to be a very, very difficult task for the pilot to stabilize such a device. So you had a joystick controlling the pitch on the 4 different corners, and the vehicle is inherently very unstable. And pilots just could not stabilize the device in air. The helicopter, as you can see on the left, is inherently easier to stabilize because you have a single large rotor above you with a large gyro effect. So that's really what stopped development of these quadcopter or drone type looking devices. And it's only since the sort of advances in computer technology and gyros, where part of the control of the device will be done by a computer, that they came back into play about 10, 20 years ago, maybe slightly earlier on the higher jump yet. So first, very simple of electronic control systems. And they have been now developed, as you can see in the lower picture there, to quite advanced and easy to fly devices. Effectively, they're flown by a computer. There's a whole lot of other types of, can you get rid of?
Yeah, I was just going to say it's actually on your machine. If you just minimize that.
Okay.
That one.
Okay, that's fine.
Thank you so much.
And so if we look, there's of course some other vertical takeoff and landing devices, like you see on the top right, a tail sitter. There's some planes that have turned the props effectively up doing takeoff and landing, and then forward to cruise along. Or you have transitional drones, as you can see on the bottom there, where you have some props propelling you forward and some props are there for takeoff and landing. Today we're going to look at the sort of smaller end of this, the sort of what we call drones, the sub-1 ton class for goods delivery or personal transport. Of course, to fly, we need a power source. Otherwise, you couldn't stay in the air. And really, the two competing technologies are gasoline or fuel or batteries. And traditionally, pretty much everything in the air used gasoline to stay up in the air. But nearly all the new proposed devices for urban transport in cities claim that they can use batteries. And I did a quick comparison here to see what is the challenge. So if I want to design a drone using batteries, then we have to limit ourselves to the capabilities of these batteries. So when we look on the left, we know that there's about 12 kilowatt hours per kilogram of petrol. So burning 1 kilogram of petrol gives you 12 kilowatt hours. You run it through your engine, maybe 30% efficiency, maybe some more or less depending on the type of engine. And you end up with about 3.6 kilowatt of useful shaft power per kilowatt of fuel. Let's compare this to the batteries. There are some experimental batteries with incredibly high power densities, maybe above 400 watt per kilogram. But in reality, when you put them into a battery pack as a product, you're well down on this. So to give you an idea, the latest Tesla battery pack, probably using one of the most advanced mass-produced batteries, is at about 160 watt hours per kilogram. So let's be a bit optimistic here. Let's say there's some more advances. Let's say in the next 5-10 years, road revolution, we can double this. We can get to 300 watt hours per kilogram. Quite an optimistic outlook, but yeah, things are developing. You can see this line there in the graph. The energy from these batteries is increasing. So I used 300 watt hour per kilogram. Of course, we have to still put this through our electric motor to convert it and frequency inverter. And I used again a fairly optimistic assumption of 93% efficient. Remember, in the global of the life, you can't have a super efficient, high copper containing, high magnet containing motor. You could be quite efficient. So 93% again is quite an optimistic assumption. So what we can see here is that the battery solution is down by a factor of about 13. So for 1 liter of fuel that I have in my helicopter, my drone needs about 13 kilograms of battery pack. And this might be a problem because, you know, when you want to fly, it can't be too heavy. Let's look, how much energy does it take actually to fly? So we want to stay in the air. We need an engine to lift us up. How much energy does it take? And there's a very simple correlation between your rotor size and the energy it takes to stay up in the air with a rotorcraft, with a device that flies below a propeller. So basically, the bigger you make the rotor, the less power you need. And that's just because the axial velocity of the fluid against which you push yourself up follows sort of a square law. Velocity square is the energy in it. So the faster you accelerate it down, the more energy you need square. So on the right graph here, you can get sort of an idea what the industry is doing. You can see that if we are on a sort of large helicopter rotor and working with this, we can get as much as 5 kilograms lift out of 1 kilowatt of power. But if we are on the bottom right there, let's say we have the Harrier jump jet and it's jetting the gas down with about Mach 1 out of its nozzles, then we need about 5 or 10 times the energy to stay airborne. And that brings us to the next problem because, as I said, let's design a drone. Let's see if this actually works. You want an urban transport drone, it's meant to park out there in the street. So size of a car would be a sensible starting point, but that gives you quite a small rotor area. So let's have a look at the extremes. So on the left, we see Atlas project. It's a project to build a helicopter that's powered by a human. Very limited power. And obviously they only achieved this after years and years of development by going with a massive rotor. You can see the picture up there. The rotor is spanning the footprint of a 737 passenger jet. And you see in the picture below the person hanging in the lines of this rotorcraft. And it's quite amazing. They managed to produce 155 kilograms of lift out of 1 kilowatt available power from the human. Right, 6.5 watt per kilogram. Not very practical for our urban transport delivery device. If we go to the other extreme, Japanese startup company using a motorbike engine, 170 kilowatts, screaming along. When you watch the video, it's incredible noisy. And here we have a device that weighs 350 kilograms. It needs most of its engine power to take off, so maybe 150 kilowatts. So you get the idea. If you want an urban transport device, you can make it big, and it needs very little power, but you make it very small, and it needs an awful lot of power. On the other hand, you also want to fly fast. And you can get the idea that the left device can't cruise very fast because the downward velocity is so slow, you wouldn't be able to get much more than walking pace from it. While this the hover bike there can go quite fast. So I tried to design a drone for you guys tonight. So sit down, let's see how big I make it. So on the left, you see standard helicopter that people might use to get from A to B. I started off making it a lot smaller because I thought parking in the road, but the numbers just didn't work out at all. So I ended up making it bigger and bigger and bigger, and got something that just about flies, by the time it's 8 meters long and 6 meters wide. So here you can see one problem is that quadcopters don't have actually very much rotor area for the footprint because a lot of the area isn't used. And you also have a lot of tip losses. Helicopter is actually much more efficient. Having one large rotor works a lot better than having 4 small rotors. So I ended up with a device that's 6 meters wide, 8 meters long. It just about fits in the road in front of here, but it's still only a 16.5 square meter of rotor area. So at the design point, fortunately you can't see the top numbers, I'm not sure if you can get anything done about it. At the design point, you need about 200 watt per kilogram to lift it up. Another interesting fact to consider when you design a rotorcraft is, so far I only talked about how much energy it takes to lift it off the ground. Of course, we don't want to just stay in the air, we want to travel along. And there's an interesting effect. Once you start flying forward, you actually need less energy. Because when you sit still, you create your own downdraft. So the whole air column in the area you are starts moving downwards. You have to push yourself faster and faster up against this downdraft that you're creating. So as soon as you start traveling forward, the energy you need is reducing, but at some point it's increasing again because you have the drag effect from flying along. And also your rotor efficiency goes down because one prop goes into the airflow, but the other one is retreating from the airflow. So inherently it's not very balanced and the efficiency goes down. So for my design here, I assume that I have to go up and stay in there. And also have to fly forward with maybe 100 kilometers per hour, which on a device like this is roughly the same energy than standing still. So we can assume that it needs about the same energy for flying at 100 kilometers per hour forward as it takes to stand still. So, you want to go home? Maybe it's two of you want to go home. Maybe it's one with a pilot. So the verdict is out. If anyone is brave enough to go into a device without a pilot, there's just a fun question on a Christmas night. If you could order your Uber Air or Uber self-driving car or Uber taxi with a driver, what would you pick? There wasn't a clear answer. I guess people would be intrigued by sitting in a device and being flown home. But then being in there without a pilot is also quite a scary experience. Remember, these things can't auto-rotate. People talk about emergency parachutes, but they just don't work if you're low. They only work when you're high up, because you need some time for the parachute to come out. And also, who would deploy the parachute? Is it the passenger on their own, just pressing a button and say, I think it sounds bad, I deploy the parachute, but you have someone sitting far afield, maybe in another country, making this decision for you. So there's quite a lot of problems with autonomous flight, because today we trust the pilot to make decisions when things start going wrong. So, a bit unclear. But let's imagine we have two people, a passenger and a pilot. So 180 kilograms for two people. Let's imagine we want to cruise along at 100 kilometers per hour, sensible speed. And then we need to look at the range. So helicopters today, 300 kilometers, 400 kilometers would be a typical range for small helicopters. Not a hope with batteries, but what's a number that would make sense, where you could say we could do something with this device. So flying from London City to Heathrow Airport, then having to recharge, maybe sort of a minimum number where you could say there's some use for it as an urban mobility vehicle. I mean, people don't like to buy the electric cars with less than 200-mile range, but let's say this thing has only 30-mile range. Okay, so summarize the numbers. We want to fly 30 kilometers at 100 kilometers per hour. It takes about 20 minutes if you allow a minute for takeoff and landing. You, of course, have to consider when you're up in the air that there's wind. And even a moderate headwind of 20 miles an hour, which is not very much, it's an average day in Edinburgh, means you already need to have the energy for 30 minutes. And then you still got to consider that things could go wrong. Let's say you've flown in the wrong direction, or yes, your landing pad has gone on fire. So there's a pretty hard rule today that helicopters must have 30 minutes reserve fuel on board in order to be allowed to fly in the UK. So you need to have 30 minutes spare fuel capacity when you land. If you go below it, you have to actually report it as an incident. You landed with less than 30 minutes to spare, has to be recorded. So let's say the lobbying is strong and we get this down to 15. Still, in my mind, a bit like driving along a busy motorway with an exit every 20 miles and having 30 minutes or 20 minutes of fuel in your tank. It's quite scary, but let's say we get this down to 15 minutes before you drop out of the air. That means we've got to design a 45-minute flight time battery into this device. So you might remember I said it's about 280 watts per kilogram you get from your battery. That's after the efficiency from the conversion. So for a 45-minute flight, it means I need about 300, I can get 370 watt from my battery. So I want to discharge it in 45 minutes. So I can draw a bit more for the 45 minutes and the capacity per hour. And I need to produce 200 watts of lift for 1 kilogram. So I need 124 kilowatt power on my device to stay airborne. And now we can just calculate out the battery weight is about 332 kilograms. So I started with designing a drone, which I thought would be the small hover bike you can jump on. Went already up to 600 kilograms. It's quite a big beast, but that's a long way from where we need to be. It still doesn't work because it's only leaving me 100 kilograms for everything else. And I don't know how heavy this drone will be, but even the most modern carbon fiber structures and lightweight electric motors are a factor of 2 or 3 out. NASA did recently a study looking at these drones, ended up with a 2-ton drone having a 700 kilogram battery in it to cover 30 minutes of flight. So I must disappoint you. I would say the revolution of calling Uber Air to fly you home is still some way from where we are today. But you might make up your own mind. And we can see these numbers with one of the leading companies developing it. On the left, you see EHAN, Chinese developer. So they got to 30 minutes. That's basically with no reserve. It's probably with 20 degrees and a high pressure region at -20 and the trickle charge batteries and everything at the best. That's how far they got. But as we know as engineers, there's a difference between an academic study and a one-off demonstration and actually having a product in the market. Because batteries do age, they're not all the same, you need to leave some margin. And Flowcopter, a German company, I think they're doing a little bit better because when you look at their device, they decided to put a massive rotor above it. So they got it down to something like only 12 kilograms per square meter loading. So they have a 40 square meter rotor. But it's not clear to me how to transport this device because it's a fixed carbon fiber ring up there, something like 8-meter diameter. So it's not exactly an urban mobility device, I would say. It's a probably quite difficult device to transport. But of course, these companies are well aware of their shortcomings. And 2 things happened fairly recently. A, these are billions of investment that went into them starting to be questioned. And all the companies, and I really mean all these companies, are now moving on. Airbus, Flowcopter, EHAN, there's 2, 3 others I found. They're all going like, okay, this is not going to work. Let's make transitional planes. Because it's just inherently so much more efficient to fly with a large wing and only using the props for takeoff and landing. So we can see a change in the market from the dream of a little hover bike to now these companies working on what's effectively full-size aeroplanes with props to take off and land. And even then, the battery only is giving them ranges of 100 miles, 150 miles, not really competing with today's expectations on aerospace. So it's not all doom and gloom. I mean, you might ask yourself why the guy who works in a drone company turns up to tell you how hopeless everything is. Because you might also remember back 10 minutes ago, I told you that fuel is about 15 times more energy dense. So if you use fuel, it actually works quite well. But then there's, of course, a dirty word, using fuel, CO2, very bad for the environment, using a petrol engine. But you also got to be very realistic about an electric plane or drone, because we all know when you make planes heavier, they need a lot more energy. And flying a battery with you costs also a lot of energy. So when you look at the actual CO2 footprint, you find that these electric drones are pretty terrible. And we can demonstrate this by having a look here. So going back to our example, 622 kilogram drone, done some basic sketches, right? And if you put a petrol engine into it and a generator, and you're driving basically the props from the engine with the generator rather than the battery, you can take quite a lot of weight out. So about half the battery weight is the engine power pack. So you have a 60 horsepower engine with a generator powering the drone. And that means we need a lot of less energy to stay airborne or to fly. So while the drone, as you calculated a moment ago, needs about 124 kilowatt to fly, by the time we're flying with petrol drone lighter, we only need about 80 kilograms for the same rotor size. We know that burning petrol produces about 3 kilograms of CO2 per kilogram of fuel. And we also know that making batteries is a pretty messy business. And the numbers of how much CO2 is emitted in the production varies widely, depends what study you read. You can get anything from 60 to 150 kilogram per kilowatt hour battery. And I went on the low end here with 80. Some people say it's 120, depends where you look, but let's assume that things get a bit better in future. So we emit 80 kilograms of CO2 per kilowatt hour battery. So it means for our 90 kilowatt hour battery that we needed for the plane or drone, we emit 7.2 tons of CO2 before we even fly. In a car, that's not too problematic because you might buy a Tesla and you drive it for 10 years and you can charge and discharge the battery maybe 1,000 times or even 1,500 times. It's like your mobile phone. It still works after 2 years. It's just it tells you battery performance 70%, 60%. Fortunately for planes, it doesn't work exactly like this. You can't say my plane is so half rusted through and I'm still going to fly because it's probably going to hold up. You got to design it with a certain spec. And if your battery decays, then you got to replace it. You can't just go flying with an old battery. And even 500 fast charge and discharge cycles, you would expect quite a significant decay in your battery performance. So some people say these are fast discharge rates. NASA had recently study, they can only get about 200 cycles where they can guarantee the performance of the battery. Other manufacturers claim 800, so I used 500 here. So it means for each flight, we have to allocate 14.4 kilograms of CO2 emission from the battery production alone. So again, we can calculate this out. Flying with my drone, 80 kilowatt drone for 20 minutes, produce about 7.2 kilograms, or needs about 7.2 kilograms of fuel, emits 22.3 kilograms of CO2. Do the same calculations on the electric drones. I've got to charge the battery. National grid is about 230 grams of CO2 per kilowatt. Some grids like in Dubai are 5 times this. Some grids in Norway may be lower, but global is more like 300-400. So I'm quite optimistic here with a fairly efficient grid, the UK grid, where you don't have much coal and lots of renewables. Still then, we end up emitting actually more CO2 with an electric drone. Maybe the solution is to cycle and not fly with an electric drone. Whatever we do flying is probably quite carbon heavy to get from A to B. Actually, in fact, using a Bell helicopter, it only needs 16 liters per 100 kilometer. So that's even better than a drone. So whatever we do here, it's going to be quite difficult to compete against the box standard Robinson R22 or Bell helicopter. When you take the numbers from them, they're even better. Some of them are as low as 10 liters per 100 kilometers of flight. So not so easy. But one thing we can do, and there might be some future in this, and I think the aerospace industry is increasingly looking in this direction, is to use excess energy from renewable production to produce hydrogen. Because we have more and more renewable energy coming on, and there are times on a Sunday afternoon when you just have too much. North Germany, often half the wind farms get switched off because they don't know where to go with this electricity. So one option is to use this to make hydrogen. And once you have hydrogen, pretty nasty stuff, difficult to transport, but you can combine it with CO2 from the atmosphere to make synthetic fuels. That's a technology which is quite expensive at the moment. It's very inefficient. But I think there are more voices in the aerospace industry saying that might be one way forward. This might actually be a more sensible way forward than flying heavy batteries around. So to source your fuel from renewable energy. And in a way, what does it matter if I put my renewable energy to charge my battery and then fly, or use my renewable energy to produce hydrogen, to produce a carbon fuel and fly with that? The efficiency from renewable energy to carbon fuel into the shaft is less than 10%. Sounds terrible, but then as we just learned, charging a battery and flying a very heavy battery is also terrible. So I think there is some movement in the market on it. The picture you see there is a recent study from the RAF. They got synthetic fuel produced, they qualified it on the Rotax engine, and did test flights in the UK. Okay, I'd like to have a short break here, because before we move on to what Flowcopter is doing, and you've forgotten all about this, I wonder if there's any questions.
Yeah, I'm interested. Did you look at how much CO2 is generated by producing the raw material? So from extraction to refining to actually coming up with a finished product.
Yes, there's a number of studies, and it depends first of all what type of hydrogen you use. I think they talk about green hydrogen in gray and black. So one way to make hydrogen is from coal, and you basically blow off the CO2 to get the hydrogen out of the water, and that's a very, very dirty process. But if you use renewable energy and you assume that the renewable energy device is already there, so let's say you have the offshore wind farm anyway, and you don't know where to go with electricity on a Sunday, then you could argue that making hydrogen is actually quite clean because the electrolyzers sitting there, boiling water, not boiling, but electrolyzing water, producing hydrogen. And then the next technique that you can use, you can either use waste CO2, so you get CO2 from industry processes that are waste, would be blown off normally, or you condense it out of the atmosphere, which in itself is, as I read, is not a perfect process. So you have to have some energy to condense it out. So there's some wastage. But I think in general, from my understanding, if you use green hydrogen, it's actually quite clean. And if you have sort of waste CO2 that will be blown off into the atmosphere other ways, you could also argue it's fairly clean. Then you combine the two into a carbon fuel, into natural gas, or you further sort of combine them. But you're right, all these processes take energy, and you need to take into account that some emissions happen during these processes. So who would fly home with an autonomous battery-powered taxi tonight? Hands up. But none of you would be brave enough to jump in one and fly home? I mean, you don't know, maybe the pilot who's flying you is, I don't know, a schoolboy in America who got a job to remotely control you. No idea.
I'm sorry, I was waving.
You would fly home.
Yeah, if I could post on Facebook about it, yeah.
Will you fly a second time or just once for the no?
I'll tell you after the first time.
Because that's also quite an interesting study I read, and that's why I'm bringing this up. We had, as I said, this guy at the Christmas party. And the market acceptance might be also a real problem. I mean, would people be happy to have these very noisy drones? And they are noisy, even electric drones, because the props are noisy. Landing in the street, flying over the castle in Edinburgh. Would people really want to be flown in an autonomous drone? And remember, putting the payload in is quite difficult. You use half your payload. Maybe you employ slim pilots, I don't know, but.
Yeah, good one. Sorry. Did you, I'm surprised you didn't mention Lilium.
Lilium, yeah.
Do you have any specific anything specific to say about that? Because I find the concept quite interesting. I mean, their ducted fan system is quite inefficient on paper, but on the other hand, it's got really good aerodynamics for horizontal flight.
Yes.
So what do you make? Where would you place that?
I would place them quite high up. I mean, I would say that a lot of companies, such as we saw on the last slide here, Flowcopter, EHang, spent a lot of time trying to make battery quadcopters and didn't get very much. And when you look at the new devices from EHang and Flowcopter here, same from Airbus, they're all following a bit what Lilium has been doing for the last 5 years, 6 years. Yeah. So just to fill anybody who doesn't know Lilium is effectively looks very similar to the bottom left here, the EHang winged drone. But instead of having big propellers to lift the drone off the ground, they have lots of small ducted fans in the main wings, and they can tilt the whole wing. So it's like a tilt wing device. And they're actually quite efficient in flight because having a distributed proportion along the wing means they can create a high velocity flow over the wing, and it's actually more efficient than having a prop pulling you through the air and then having the airflow hitting the wing profile. So I would place them personally quite highly because they are maybe 5 years ahead of where a lot of the other guys are now going. And I think they are looking at electric planes, you could say, but it's a long way from urban mobility because I don't know if they have 20-meter wingspan. I mean, they're not landing on a helipad. And remember also, they have quite a lot of area for wind to attack. So while on a very calm day, they could probably drop down in a quite small footprint, in gusty, strong wind condition, any of these hybrid concepts need to fly into the wind forward to stabilize themselves and then slowly lower themselves. But that means the landing area they need is effectively a short airfield. Because you can imagine if you have this massive wing folded up and you get hit by a 40-mile-an-hour gust, before you know it, you're 100 meters off your position, which is different with the drone devices. When you look at the top drone devices, they can actually land in quite strong wind conditions because the area of attack is quite small. So, but yeah, this is probably what we would find at some point to fly, I don't know, out to Orkney from the mainland, or where people offer short or medium length flight, but they probably go from airfield to airfield, not from back garden to back garden. Or as we've seen the example tonight out of the Royal Scots Club here, picking you up this Uber Air to take you home.
Does this get in with sort of consumption you get out of a microlight?
I guess the microlight, and this is just, I don't know the exact answer, it's probably quite good because it will have a very large area, wing area per bake, which makes it good. It doesn't go too fast, therefore. I would assume the microlight has, I don't know, a vortex engine with 20 or 30 horsepower, pushing you along with maybe 50, 60 kilometers per hour using 5 liters. So I would expect that the microlight is much better than any drone device. In general, wing devices are just better. Having a large wing area and flying through the airflow is just a much more efficient way than lifting yourself on propellers. I know that Rotax makes small microlight engines. We studied them early when we looked at our drone concept. And yeah, they're quite efficient. I mean, they're sort of 30% efficient. So my guess would be they're quite efficient in terms of passenger mile CO2. So a car is, as we know, like an old big car might be 150, 200 grams per kilometer. And so electric cars now, by now 50 or so, if the grid is not too dirty. That Robinson helicopter is about twice what a big car is, so maybe at 500 grams per kilometer, maybe like Ferrari. Driving a Ferrari and flying a Bell helicopter is probably the same. But then flying out of electric drones is definitely much worse than the most polluting sports car.
Ryanair reckoned about 85. Ryanair reckoned about 85.
Yeah, that makes sense. Big airliners.
She's critical.
Yes. So if you don't fill your seats, then you're probably behind.
I was just going to say that if anybody has questions online, I have put them in the chat, the questions that have been asked. But if you have questions online and you want to ask them, maybe what we do is we add them up towards the end of the talk and we bring them back there.
Yeah.
But,
Also, we're a bit behind schedule, and I haven't even talked about Flowcopter. So let's move on to Flowcopter. So, on conclusion from our earlier discussion, we decided to go with a petrol engine. We know we have a very efficient transmission technology, so we can transmit power from the engine to the props. I'll come to it a bit later. And the first thing we did, we're looking at different engine options. And on the left here, you see a Rotax petrol engine. That's what you might have in a Cessna aircraft. So we studied this quite carefully. We also looked at diesel engines, diesel piston engines for planes, because if you want to fly out to, let's say, a wind farm or so, they don't like having petrol being out there, so they would prefer to use diesel jet fuel. So you can see the next engine, the Continental, is the equivalent engine. It's a bit heavier for the power, but then you need less fuel per hour. So on a longish flight, it works out pretty equivalent. And then you can also look at turbo soft shaft engines, but they're very inefficient when they're small. Some of the inefficiency is compensated by the lower weight, but still the fuel consumption is substantially higher flying with a small turboshaft engine. So the fuel consumption per power, as you can see here on the bottom line, is nearly double that of the diesel engine. And the extras or the saving of 40, 50 kilograms of weight don't really work out. And that's not even including the gearbox. These engines spin very fast, so you have to add a gearbox. So we felt that we couldn't get there to where we wanted to be. So we ended up designing around this Rotax 915 engine and the Continental CD135 engine, both about 100 kilowatt. So using this engine, as you can see on the left, we combine it with what we call a digital displacement pump. It's a new type of hydraulic pump that's very efficient, very controllable, and also can have multiple outputs that are independently controllable. So brought you some samples, this 3D printed one in, to get an idea what we're looking at. It's about the size. In cast iron, it's about 45 kilograms. You could probably make a lightweight aerospace version, about 25, 30 kilograms in weight. And this pump here can convert the full 100 kilowatts from the engine into fluid power. And it can independently control 4 outlets. Conversion efficiency is around 94, 95%. Much more power dense than an electric machine, and also a lot cheaper. It doesn't need an inverter controller for it. And in production, you're only looking at a few £1,000 for a machine like this, compared to very expensive electric machinery. So we then combine it with a hydraulic motor. So you see a picture here. These little bent axis machines can convert the fluid power back into shaft power. You can have more to run in, so you can visualize what they look like. It's 5.5 kilograms in cast iron, probably about 3 kilograms, 3.5 kilograms in a lightweight body. And it's impressive. This machine here can output about 60 kilowatt. And it can output 30 kilowatts very efficiently, continuously. So we have a drive, the size of my hand here, that can drive a 30 kilowatt propeller. So, as I said, propeller, we can connect this to propeller. That's a 1.6 meter. For the drone we are working on now, we're at 1.8 meter, but that gives you an idea on the prop size. So these here are a good pair. They can convert about 30 to 40 kilowatt if you push it, and lift over 100 kilograms. So something in my hand here, which is only 7 kilograms, and it can lift 100. So the power to weight ratios are incredibly good in hydraulics. And you can also see this because these machines are designed and used in forestry equipment to power big chainsaws on forestry machinery. They're used in all sorts of very harsh environments. So not only have we got a transmission technology that's very light, very low cost, but it's also very robust. Of course, you need to connect them to each other. And if you use hydraulic hose, again, you get lightweight versions. So that gives you an idea on the scale. That's an efficient way to connect the pump with the motors. And that's pretty much it for our transmission. So we have an engine, a pump, 4 hydraulic motors, 4 propellers. There's a bit of balance of system, a filter, and some hoses. And of course, we need controllers for it, but they're fairly lightweight. So when we sum the whole lot up, we're only at about 180, 190 kilograms for a 100 kilowatt drive system. And now you see the numbers start to work out much better, because we could probably lift up to 500 or 600 kilograms with this arrangement. So our complete powertrain is only a third of the total device weight. We're currently designing for a maximum weight of 380 kilograms to give us some headroom, some margin, but maybe in the future can push this a bit further. Fuel consumption is about 13 kilograms per hour. So again, when you work it out in CO2, it's not terrible for a 400 kilogram device flying. Could probably be a bit better. If you use a diesel engine, it comes down to about 10 kilograms per hour, but that's roughly where we are. So picking up again from where we were in Artemis, when we developed this technology, we bought over by Mitsubishi Heavy Industries. We started developing a large wind turbine, got all the way up to a 7 megawatt transmission. And Artemis is a quite inspirational place. And people had lots of ideas making pumps for American Cuppers boats and for all sorts of wacky applications. And Neil Caldwell came up with the idea to put it in a drone. He said people were smiling initially a little bit, but then doing some numbers, it turned out that it's actually quite an attractive arrangement. Next question that people had, is it actually controllable? Can you actually control a drone with such a transmission? And to answer this, we built a small test rig. So what you see is a surfboard mast. On the mast, you see a small hydraulic motor, smaller version of this one, and a small propeller of about this size, half the size or the area of the full-scale one. And we said, let's see if we can fly. Because if we can fly this weight on an arm in a position, then obviously we should be able to fly a drone, which is just having 4 corners. And you can see in the video that we can control it on the lower weight point. We can then do a control demand and put it into the upper weight point. But we also need to be resilient against somebody upsetting the system. So we had a special technique to trigger some gusts, which you will see appearing now. Somebody came with a broom and hitting it. But you can see the control system is always bringing it back to the target position. So that gave us a sort of confidence that, yes, our pump can control the rotor speed to stabilize us in the position we want to be in. Next question was, can we scale it up? Can we make it to the size it's needed? So here you see the next arm. It's now a bit more beefy. It's a large aluminum substructure. And on the luggage belts there, you see some cast things. We loaded it up with about 85 kilograms of lift weight on the outer end. And now we're going to the full scale. So the motor I showed you a moment ago is a larger propeller. And we said, can we lift 85 kilograms and stabilize it? And again, it pretty much worked out of the box. We got it to fly. So it's sort of nicely stabilizing it with the heavy load. Again, one comment on urban air mobility. We had this one running what we call building 3, which is a long way from the office at the front, I don't know, 100 meters. And the people in the office were complaining about the noise. These props are noisy. Once you have a tip speed of 150, 200 meters per second, the aerodynamic noise is like this booming noise. It travels. It's a bit like sitting in the airport when one of these sort of like flyby prop planes takes off. You hear this booming. So it doesn't matter if you're electric or an engine. Most of the noise really comes from these propellers. Having a sort of confidence that we can make it work, we can control it, we can scale it, the rate is good, we decided to go forward with this project, but Danfoss had bought us at this point, and being a hydraulic company, delivering pumps and motors to large OEMs such as Volvo and Liebherr, it didn't really fit their portfolio. But getting together with a couple of colleagues, we said it's just a too good opportunity to pass. And on a summer evening, sitting in my garden, we brainstormed on it and ended up sort of applying for a limited company, opening a bank account, getting the web page set up, invested our savings into it, and started a company. Sometimes students ask me, how do you start a company? It's actually quite easy. You just sit down and do the registration and get your web page and open a bank account and put some money in. That's the easy part. But that's when the work starts. It's then a very, very hard and challenging road to go from this startup company with no facilities and nothing to actually a business that starts to function in terms of making money. So we looked at the drone market and pretty quickly concluded that urban air mobility is interesting, but as I said, the numbers don't really add up. As you can see on the bottom right there, the drones, electric drones we have today, they're either nice small toys, or they're sort of quite expensive and quite limited in their range and capability. What we decided to really look at is industrial applications. We wanted to produce something that can do what small helicopters do at a lower cost. So applications where today you use a helicopter to fly out a spare part to a wind turbine, to do Coast Guard service, to do all sorts of industrial applications where helicopters are used today. And that's what we call ourselves an industrial heavy lift drone. So we are very much focused on designing something that's not too expensive, that's IP rated, that's serviceable in the field. Because when you look at most of these air taxi devices, they have open windings out in the props, the carbon fiber shells. They're actually quite flimsy, fragile devices. We decided not to go down this route. We decided to go down to address the real need in the market that we see for a cheap version of a helicopter. Because a lot of helicopters just fly out to look down or to transport a small part. We then looked at what business model do we choose for the company. And of course, we can just write a patent and try to license it, or we can just try to make drones. And we decided to keep, initially at least, the sort of assembly of the drone, the testing, control system development, and the core IP in-house. So we can mature it in the company, we can make the inventions in this field, we can patent them, we can grow the company at the technology readiness level up to maybe 5, 6, make demonstrators. And to do this, we have to rely on strong partners, suppliers. We're working very closely with Rotax on the engine. We're working with Danfoss on the hydraulics. We are in touch with a number of flight control system developers, all the way from sort of hobby-grade pickups to very expensive commercial aerospace sort of rated flight controllers. And so we are working a lot with suppliers, and we like to focus on what we're good at, which is a transmission. So we like to focus our team on developing the transmission, and then hopefully use partners and suppliers to do the subsystem. Initially, we're looking at markets that are relatively easy to get into. I'll say some more words about this later. But in the long run, of course, there's different exit strategies from the company. We could either be bought over by a large company such as Airbus or license them. Who knows, if it works, they might take interest in us. We could work with a smaller sort of like player who wants to make machines for Coast Guard service. So we are quite open on this, but for the next couple of years, we want to mature the technology inside the company. And for this, of course, we need money. So we're looking at the moment at a combination of government funding, some small amount of money from the Scottish government. We raised some money between us and friends and family. We raised some money from a VC in America. And also we are now engaging with one customer who is starting to, or is planning to give us some money to make a demonstrator. So we're trying to have multiple income streams, both soft and hard money in this one. Next step, once we had the transmission demonstrated on a single arm, is to make a device. So we decided not to invest a lot of time into carbon fiber structures, keep it simple. We just welded up the device. So we just bought aluminum tube, welded it up, not with a view to fly it, with a view to assemble a complete system and operate it on road cells. So here you can see the complete assembly. Again, it's not a sort of beautiful demonstrator for the public. It's being out in the shed near the airport, no heating, freezing cold in winter, running the engine. But you can see the device, or just about sits on 4 load cells, so we could operate it and measure lift, measure response speeds, measure efficiencies. We then sort of took it out into the field to make something that's a bit better of a picture to raise more money. But yeah, it's pretty much still in the early stage engineering work. At the moment, we're operating this machine with an electric motor in our test cell. We moved in the meantime to Lone Head with a better facility there. And we're operating it in a test cell powered by an electric motor. And we are now sort of collecting a lot of data. How long does it take to go from lift point 1 to lift point 2? How much heat is ending up in the oil to size the oil coolers and so on, vibrations. So that's where we are at the moment. So we're operating this device on test. So what's next for next year? We need to start flying. We're growing the team and some engineers. And really the mission for next year, target is Easter, to have a device that we can go out with and fly. It's quite difficult to get permission to fly in the UK from the outside, but you don't need any permissions to fly inside. So we're thinking initially to go into an old farm shed or old building or put it on a tether. And we're planning to make a device that we can operate out to demonstrate the capability. We've done quite a lot of research and thinking on how we actually design the frame to suit the application. You see, the first one we made was this welded aluminium, which is easy, but actually quite not very strong, because once you weld the aluminium, you lose the temper in the aluminium, strength goes down. So it's very difficult to inspect. We had a crack in the first test run we made. So that's why not many aircraft are welded together, because you want to use a 70,000 series high-strength aluminium. That doesn't lend itself to welding. You have to use a softer grade, and after welding, it's even softer. So aluminium is actually not very strongly welded. We then moved on to looking at a riveted frame. Sample we made, and we concluded that a riveted aluminum sheet metal frame, as you might find in light aircraft, lends itself very well to have large areas with load, but we have largely point loads on the interfaces to the motor, to the engine. So the structure became very complex. Thousands of rivets in our sort of model didn't look very sort of promising. Of course, we could down the route like other people do, making a full carbon fiber device. But again, we want to go in the industrial market. Having one single large piece is difficult to ship. If you damage it, imagine the farmer takes it on the trailer and puts a scratch into it. You have to scrap the whole device. Again, we feel that's not really the way forward. And on the conclusion of this, we decided that just do what helicopters do. We have a steel frame, very easy to weld, it's very strong, and you can inspect the weld relatively easily. You can pressurize the frame and have a pressure sensor. So if you get a crack, the pressure drops, you know that's a hole in the frame. And we go with a fairly simple welded steel frame, pretty much copying from what most small helicopters do. But then for the one task, which is the arms that take the motors that stick out, you want to be quite compact, do not have too much aerodynamic drag from the propeller going down. And we decided to go for carbon fiber on this one single component, having a separate removable component. So here you can see we did an initial test in the bottom right here, where we mounted one of the motors against the steel frame, put the prop on, we operated it to pull it. We're monitoring vibrations, we're monitoring deflection. That's the sort of tube we're using. It's quite impressive. You can take a meter of this tube and we try to break it. We put 300 kilograms, 3 times our design load on that, and it still wouldn't break. Couldn't put any more on without testing it up because the aluminium that was holding the tube broke at some point. So it's quite impressive, this stuff, but also, as I said, it's quite expensive and fragile, so it's easily damaged. But we decided to go with 4 carbon arms for the device. Then will look probably something like in the top picture. It's the early version of it, but you have a steel frame, carbon fiber outriggers with the props, and a glass fiber cover around it. We've done a lot of market studies, talked to a lot of players from Coast Guard services to Leonardo helicopters, Babcock. We talked to firefighting people, to all sorts of people that might want to use a helicopter. Often a lot of cold calling, LinkedIn, finding people, ringing them, hustling them. But that's how we learned a lot about what the market is actually looking for. And I sort of placed them a bit on this sort of roadmap that we have. So you can see on the bottom here, tree planting and crop spraying is where we want to start. I'll explain to you in a moment why we picked these ones. There's maybe offshore logistics like wind turbines, need support, search and rescue. Maybe further afield, we have delivery services, flying stuff out to remote islands. And really sort of piloted and self-flying air taxis to me are far over the horizon. Maybe that's something that we can look at again in 10 years, but right now, I don't feel that that's a market that suits our design and device in our company. Yeah, for the military to the left there, it's fallen by the wayside. For more personal reasons, we decided to not get involved with any military applications. Sure, the military would love our technology and there's probably a lot of money, but there's very strong personal feelings with the top directors in the company that we are not engaging with any military applications. We might go as far as security, such as of Coast Guard services, policing, but definitely not into stealth and weapon operation. That's clearly a no-go area for us as a company. So, which one did we pick? Tree planting. You might know tree planting, but what's tree planting? Why would you use a drone? But it's quite interesting, and it's always when you get into an application, you learn more and more about an application. So first of all, I believe tree planting is quite a good thing that we should be doing. And of course, we could say we should have more trees to sort of make the planet a better place. But I wouldn't even go so far. I would say we should sort of like stop losing so many trees. Because at the moment, we are losing a lot of trees every year. And there's different reasons why we lose them. One reason, of course, is people cut them down for timber, might burn them down for agriculture land, I want to build buildings and bridges. And it's quite difficult to fight with them because obviously they have their reasons why they want to cut it down because they want to do something else there. And it's probably quite difficult to stop this happening. But then there's a lot of forest loss from forest fires. And it's significant. Last year, about half the size of the UK equivalent burned down between Canada, North America, and the US. So there's vast areas of forest that we lose every year with forest fires. And it seems to be increasing with climate change, hotter temperatures, less water. So we seem to be losing more and more. And there's a number of companies that are now picking up on this. And what they sort of like looking at is to automate the tree planting, because it's fine to go out with a bunch of students and pay them some minimum wage and get them to plant trees. Promise they don't come back next year because after you planted trees and you burn down forest for months, you know that's not what you want to do for the rest of your life. And the number of people you would actually need in North America to replant what has burned down there in the last year is just totally disproportionate to how many people you could hire to do it. So replanting these remote forests that burned down by hand isn't very feasible. Going in with machinery is also very difficult because it's often very rough terrain, there's no roads there, it's very difficult to go in on the ground. So there's a number of companies, Dendra, Flush Forest, Drone Seed, a number of companies that are now sort of looking to do tree planting automated. So I mean, automate, they want to drive out with a pickup truck, that people maybe doing some manual planting, they might fly some seedlings out where other people are hand planting, they might plant some from the drone. So basically using drone technology for support in the tree planting. And they also have now a lot of success with automating tree planting. So what they do is they have vision recognition systems that can fly over a burnt down forest and can first of all detect where there's a good area to plant. So there's no point dropping them on rocks. So you need to find the best spots to plant them. And they have also developed some seedling pots. So you put the seedling into a little pot, you have it germinated already, or you have just the seed. The pot contains some fertilizer, some water absorbing material, and you drop it onto the soft soil, and the tree will start growing in your pot, and then later root into the ground. And they don't get the same success rates as you might get from hand planting, actually getting in the ground, but they get really good success rates. And so that's seen as one way forward. So we now started a project with a company called Drone Seed. They're Seattle-based, but they're also really looking into replant in Canada and the US. And they have sort of like at the moment we're finalizing a deal to deliver first drone demonstrator later part of next year. And then they have sort of a letter of intent to order more drones following here after a successful demonstration. So that's roughly where we're going as a company at the moment. Something I believe in, something I quite look forward to. Test it out in Nigeria. Service our drone the next 12 months. So, thank you.
Well, thank you very much. Thank you very much. I guess I'll invite one or two very brief questions if there are any. I think we've had an amazing tour de force there of the drone world and the rationale behind your design, which I thought was fantastic. So can I take one or two quick questions, if I might? Do we have any? Or have we answered them all? Jonathan.
Just the software they use for electric drones, for small, toy drones, can that software scale up? Just the control system, the control algorithm, so they're applicable to large drones?
Yes, they're fully applicable. We are using at the moment for our sort of development, sort of like best version toy software, you could say, which is sort of autopilot with a cube processor. It's based on what used to be called the Takeoffs. In many ways, they are ahead of the expensive commercial controllers. So what you find is the companies that make sort of Calinens or Ethereum or so, that make sort of commercial drone controllers, and they're very robust and redundant, and they have very good IP rating and connectors, but they're not half as good as the sort of mainstream open source Takeoff cube controller, which has been flown in probably 1 million drones, and people have contributed to and developed. So it's a bit of a tricky one, what controller to pick. You can have the really cheap, bit of hobby grade hardware, is a very good software, or you lock yourself into one of the sort of commercial providers that's probably quite behind the curve on it, but provides you with a very robust hardware and also a qualified software that you can go to the authorities with and get certified. So we decided to actually stay with the Takeoff's Cube controller for now. And the logic of control is just the same. It doesn't really matter if you control the flow from our pump, which can take CAN bars or PWM signal, or if you have your speed controller on your electric drones. So we don't have to develop anything new there.
Well, that's great. I might leave any final questions if you're happy to approach the speaker afterwards, I think, because we're a little time, but what a great tour that was of, first of all, could we go home in a drone? Unfortunately not. What a pity that is. Although personally, I'm quite happy to walk back without trying to take some autopiloted thing that's 3 times heavier than the because of the battery that's in it. So no, what an interesting presentation as well to touch on the physics of why you chose what you chose in terms of building the Flowcopter, walking us through the rationale for hydraulic design, taking the advantage. I mean, you could do a whole series on the advantage of 3D printing, but I mean, certainly invite everybody to have a look at what looks to me like a very complex manifold here at the front that evidently weighs 5 or 10 kilos in comparison to something that would be 50 or 60 kilos of steel. I mean, that's a revolution in itself. And then you have 60, 100 kilowatt transmission device that weighs, can fit in a hand. John.
Pravas is going to say a few words.
Sure. Okay, yeah. Well, I might need to do that. Yeah, go ahead. But I'll just sign up from me. I really enjoyed, first of all, that, but also talking through the commercialization that you've also discussed. I'm involved a lot in starting new companies. It isn't an easy journey. You do have to put yourself really all into it. And like you say, starting a company is the very easy bit, but following through, building, commercialization. Fantastic to hear that you're approaching all these different markets and thinking about how to bring this to the world. So thank you from me. And yeah, please do say a few words and we'll close with that. Thank you.
All right, just a quick word of thanks. First off, a big thank you to everybody who came here physically to support and to view this talk. A big thanks to those who are online as well today. And of course, biggest thanks should go to Professor Uwe Stein for such a fantastic talk. I was actually torn at one point between, whether I liked the talk more or the fact that I thought he picked up a 60-kilo lump of metal with one arm. Who knew that, something that was, started being designed in 1923 would end up being driven by children at about that size 100 years later as well. I thought the comparison between, the CO2 output as well when it came to the petrol and the battery is very interesting. There are many other factors, of course, that are of interest there. For example, the way in which the heavy metals and the precious metals are extracted and how they use them. Do we have enough of that kind of stuff as well? So there are many things to think about, and I think that Uwe has covered many of those and many more, and perhaps we could end with a round of applause for Professor Stein for the fantastic talk he gave us today.
COVID permitting, our next talk will be on the 11th of January, and it will be on the future of 3D printing space telescopes. So slightly space themed, but not to do with lifting, but to do with seeing what's up there. So another fantastic opportunity to engage, and we hope that will be in person and online. But if not, I suspect we will do it online. And thank you everyone for working with us on the Zoom and for sticking with us on that, and everybody for being in the room here as well. On that, we will close, and I'll close the Zoom call. Thank you everybody. Thank you.
Going to be difficult by other people.